play. All right. I don't know. Yeah, I was kind of wondering what's going to happen. All right. So it is, in fact, National Find a Rainbow Day. So make that your goal for the day, perhaps, or don't. I mean, whatever makes you happy.
Wait, isn't it?
Probably. There are a lot of them. That was just
No, I heard something.
When it comes to you, let me know. All right. It's also Sam's dad's birthday, so that's pretty awesome. All right. I want your attention up here, guys. We have a lot to do, and we have to get through stuff. So today we're going to do polarization. We're going to finish it up. That's the stuff that we started yesterday that blew over their minds. Whoa. We're going to go through a little bit more today. We're going to talk about the Doppler effect, and we're going to try and get to color today, which we'll see how that goes. Tomorrow, our plan is to finish color and do any review that you would like. All of this is conceptual. All the stuff that we've been doing, just talking about light waves, the EM spectrum, polarization, Doppler effect, color, it's all conceptual, but it's all important in good physics. And we're going to quiz over that on Friday. Okay? So it was supposed to be tomorrow, but I think we need one more day to make sure that we're feeling good. So we're going to quiz over that stuff on Friday. Yeah.
When do we retake the other quiz?
Come in whenever you want. Yeah.
Well,
but
we're doing that extra practice.
So the way I'm doing it is just make sure that you have your homework done, show me your homework,
Okay.
and then make corrections on your quiz.
Okay.
Yeah. So, and then you can come in and take it. I've got it. I got it written last night. So anytime that you would like to come in this week, I would prefer, if possible, to get your retake done just so that we don't have to draw it out forever. But if that doesn't work, let me know. Okay. So how are we doing? Are we okay? Yeah? All right. So I'm going to get out my polarization stuff. I want you to get out your polarization notes. And if you were here yesterday, I want you to look back at those pictures that you drew so that you remember what we were talking about. We said yesterday that polarization, or that using a polarizer was kind of like a gate, a slatted gate, okay? And we got out the projector. So I'm going to pull my projector back out, my real projector, my overhead projector, okay? You got your notes out? You had your pictures of polarization yesterday. And yesterday we did a couple of things I just want to remind you so that you're aware. So we said that electromagnetic waves look like this. Okay? Do you remember what this picture showed you?
Magnetic field that's all perpendicular to each other.
So there are three pieces, or two pieces really, to an electromagnetic wave. If you look at the word electromagnetic, it will give you a big hint. There's an electric field and there's a magnetic field, and they are mutually perpendicular to one another, and they're also perpendicular to the wave motion. So the wave is moving perpendicular to both of those, and they go in one of two directions, or one of an infinite number of directions. But the electric field, if it's going up and down, the magnetic field is going this way. Or it's going like this, or like this, or like this. It could be rotating in any direction, but that is what an EM wave looks like. So then yesterday, I don't remember, did we look at this picture? I can't remember if we saw this one or not. So the way that this works, I'm just going to pull this down so you can see it a little bit better. Okay, so this wave over here, the thing that's kind of like a flower pinata, something, is really just showing that you can have electromagnetic waves that are aligned in all different directions. Right? So you've got all of these different directions, but once it goes through one of these pieces of polarized film, okay, which are basically just having lots and lots of slats, it lines them all up, okay? And so that's what we saw here. So I'm going to go ahead and do this. Just kind of transition one to another to the other today. So I've got... That's really annoying, sorry. There we go. So the light that's coming out of the lamp is unpolarized, right? It's all just going all which way, okay? Some of that light is polarized up and down, and that's the light that comes through here. The light that's polarized in the horizontal direction cannot get through. That's okay. It's about half of the light. So about 50% of the light goes through the gray one that goes through the white. The interesting thing is that when we have this, then if I've got two of them, okay, these are both oriented in the same direction, both upwards. And if I move my hand right here, then these are really just the same color. Okay, so they're really just the same color. But that's not as interesting as, so these are vertically. But when I start turning this, what happens in that overlapped part? It gets darker. So when I put it exactly perpendicular, then what's going on here? Okay, what happens? It's dark. How much light is getting through? Zero. None of it. It's not happening, right? So I could do this again. I could do this in a different way. I've got this other cute little thing. This one I will just sit up here a little higher, and I think that we can see pretty much the same thing here. So I've got that, and that's all dark. But if I turn this, whoop, right? You see, so I just got a piece of Polaroid film that's up on a ring stand, just so that I can sit here nicely, so we can see it better, right? Like that, and then like that. So same.
Whoa.
Does that make sense? Are you with me there?
Yeah.
Yeah. So this one is just covering up all of the light, which is why it doesn't look quite the same. Okay. So on your picture, I'm going to go ahead and draw this on my board as well. Turn this on just to make sure that you are at the same spot that I am. If you've got one piece of polarizer that's oriented like this, that means that all of the light that's oriented up and down can get through. And again, we said this yesterday, but just to be very clear, if I have a wave of light that's oriented like this, is it going to get through the pink one?
Yeah.
Some of it will, right? And it depends on the angle. So some of it will. The part that's going up and down will get through, but the part that's going horizontally will not get through. Okay, so if I've got another one that's like, whoops, like that, then most of it will get through, but not quite all of it, because I've got some of it that's going to go like this, and some of it that's going to go like that. And so only the pink pieces, only the vertically aligned pieces are going to get through. All the blue pieces will not. So if I have a ray of light that is only in the horizontal direction, that light will not get through. So these blue ones will not get through. Okay, so I'm going to take another piece of polarizer oriented in the other direction. So I'm just kind of illustrating what we had there, just making sure that you're all with me here. So this polarizer is oriented horizontally. Okay, light that's going horizontally will be able to get through, but light that's going vertically will not be able to get through. Okay, but again, if I've got another one that's a little bit of and a little bit like this, right? The horizontal part will be able to get through. The vertical part, no. Let's cross that part out just so we're really clear. And the interesting thing then is that we're going to have about 50% of the light that gets through this one, 50% of the light gets through this one, and how much gets through here?
All of it?
All of the light gets through here?
Or no?
None of it. So this one is at about 50% of the light, 50% in this section, and this is completely dark. So I'm going to put a layer. Hold on just a second. So no light gets through. Come on, thing. Here. Yeah.
Why are we making those triangles?
Just to show, because the light in our picture over here is going in all different directions. So the light that's coming from the lights, the light that comes from the sun, the light that comes from my projector is unpolarized. So that means that the electric field is going in an infinite number of different directions. So each individual wave is going this way, or this way, or this way, or this way. So it could be like the orange one, or the green one, or the blue one, or the pink one. Does that make sense? But all I'm doing here is just taking the components.
There are many more arrows of that.
Yes, there are tons. There are tons. I'm just picking out a few.
Okay.
Yeah, and if I do this, let me just, to be very clear. So I had this set up like this, right? So now the orientation is vertical. But if I flip this, like, or if I turn it like that, now the light that's getting through this polarizer is like this. Does that make sense? Okay. But the reason that as I turn this, just this one polarizer, it's about the same brightness, and by about, I mean exactly the same brightness, is because 50% of the light is getting through all the time. Okay. But then when I put this one on, they all get through, or 50%. So 50% is getting through everywhere, and then 50%, but it's a different 50% than here. And then that one is nothing. Okay, because if I hold this up higher, it's a little bit easier to think about. I've got light coming from inside the lamp. It goes through this one, oriented this way. So now all of the light going through this one is oriented vertically, let's say, okay? That vertically oriented light, when it gets to this polarizer, cannot get through. So it's going to be stopped. So all of the light that goes through here is going to be stopped by that. Is that feeling okay? All right, cool. Okay, so there we go. Okay, so then we talked about yesterday also just a couple of other little things that I just want to make sure make sense. We talked about how we can use this, we can, what do I say? Utilize this fact with polarizing sunglasses. So the super cheap sunglasses that you get at Walgreens are generally not polarized, right? Like the $5 sunglasses, just pieces of gray plastic, okay? But sometimes you can find, very rarely do you find them at Walgreens, but if you get like fancy sunglasses, like not just the ones that have like a fancy name, but the ones that are expensive because they're better, most of those are polarized. And the reason for that is that when light is unpolarized that comes from the sun, when it hits a surface, the reflected light is all polarized horizontal, or is parallel to that surface. So that means that all of the light that's bouncing off of whatever surface it is polarized this way, horizontally, okay? And we want to cut that light, that extra glare. So that means that we put our polarizers vertically.
Just a little bit.
What's that?
Just a little bit so that we can still see though, right?
Right, so do you remember yesterday when we were doing this and we flipped and flipped and flipped and flipped? You can still see through it because most of the light that's coming through is unpolarized. It's just that glare.
Okay.
The glare light is polarized, and that's the light you want to cut. Yeah. So if you have polarized sunglasses, or if you ever have an opportunity to see them, and you're walking and you see glare and you tip your head and you start walking like this, people are going to look at you funny, but you can also see that the glare comes back, and then it goes away, comes back, yeah. That's why you don't wear your sunglasses on the side. I don't know who would do that, but yeah. We also said yesterday that LCD displays work on this as well. So in my old car before the one I have now, it had a nice LCD panel that displayed like how much fuel I had and blah 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 blah. And I was actually in the passenger seat. My husband was driving, and I was wearing my polarized sunglasses because I had them at the time before I had broken them or lost them or whatever happened, right? And I don't know, like I must have turned my head. I don't have any idea why. But as I did that, the display started getting really funky. It got really weird because even though it was a super fancy LCD display in my car, it still uses the same principle. And so there are some different things with the color and but it's the same idea. Okay. The other time that you sometimes see them if you're wearing those fancy sunglasses is that some cars have like a polarizer on the windshield so that it helps to cut down glare as well. And so then if you're looking through your fancy sunglasses, you can actually see lines like big bands in the windshield. So lots of times to see them. So that's all well and good. Oh yeah, go ahead.
Would polarized sunglasses, so if someone has a watch on or their phone's out and the light's bouncing off, would that be considered glare? Would that be polarized?
Say that one more. Okay, say that one more time. I wasn't quite
so
processing.
If you're in a car and someone has a watch on and they have their phone out and the light's bouncing off and hitting you directly in the eye, if you put on polarized sunglasses,
that glare will be cut. Just like when we were doing this yesterday and we were looking at the glare coming in, and it's the same deal. Yeah. And that's true of not just a phone, but any surface. Any flat surface that's smooth is going to have that glare. Yeah. So I like that. I think that's cool, but there's more, and this is the there's more part that I want to share with you. So I had my polarizer here, and I had my polarizer here, and now I'm going to add some more fun to the story here, but I need to figure out how to do this quite the perfect way. Maybe go like this. Maybe that'll be the perfect way to do it. We'll see. I haven't tried this. Oops, I guess I had to turn my projector off. I'm going to pause because this is not going to be interesting for my friends that are not here. Sorry, you're missing the cool part. Okay. Whew. So polarization, you got it? You get the ideas? Everything's good? I should have. I think about doing that. Maybe I'll do that next period. I'll try to remember to get that to happen. Yeah. All right. Next thing we're going to do is talk about the Doppler effect. Have you heard of the Doppler effect before? You've heard of Doppler radar. You have. What is Doppler radar? What do you use Doppler radar for?
it's like it's going to rain, or if it's just going to do any type of thing with weather.
Right, so they use the Doppler effect. Now, it's not like Doppler radar tells you what the weather is going to be. But meteorologists use Doppler radar to measure how fast clouds are moving. That's essentially what they do. So they are sending out signals, waves, and those signals bounce back, just like a bat does, right? Same kind of deal. Echolocation, it's the same kind of deal. We're going to talk about Doppler effect from a very simple perspective to start. And I'm trying to decide. I have a video that I think I'm going to show you the video first. I think that's what I'm going to do. I will tell you that when you're doing the homework from this, it's actually in the sound section because a lot of textbooks teach it in the sound section. I like to teach it in light because I like the light applications of the Doppler effect even more than the sound ones. Sorry, I'm debating. I'm trying to decide if I want to do it this way. We're going to just do it this way. We're going to do the video first. The guy talks kind of fast, so I'll pause it partway through to make sure we're doing okay. No, I don't think that would be effective. I don't think that's what we want. All right. It's a 3-minute video. He says everything that we need to know.
In Sheldon's words, it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this.
Okay, so far so good? Does that make sense? So when we talked about we had the tuning fork, it's sending out waves like this. If you have a light, it's sending out waves like that. We can always draw them this way. There's a whole section in your book, and in a lot of physics teachers go through this whole thing about spherical waves. I'm kind of taking it for granted that makes sense to you, that is understandable. So it's not going out in just one direction like when I had the slinky, but it's going out in all directions. And they're equidistant in all directions because it has the same frequency in all directions. Okay? Just making sure we're okay.
Even if you talk one way, it still goes the same.
Yep, so it'll go this way, it'll go this way. Yep, it goes all directions. Mm-hmm. Yeah. So it's a little bit different if you're talking in this direction because my sound is aimed in that direction. But if I stand like this, you can still hear me, right? Yeah. What did you say? Yeah, because my sound still moves in all directions. Does that make sense? Yeah. Good question though. All right, let's keep going. Oh, maybe. What did I do? Broke it. Play.
We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
How are we doing so far? Does that make sense? So in your notes, there's actually the page that we did comparing light waves on the back of that page. Pull that out right now. We're going to take notes from this guy. I feel like that'll be a good approach here. So don't draw the picture yet. We'll get back to the picture in just a second. But what I want you to write down right now is, I think I've got this here too. There it is that we know that what causes the Doppler effect? What did he say? Do you remember? Yes. So when an object emitting a wave moves relative to an observer. When an object emitting waves moves relative to an observer. And we're going to adjust that in a little bit, but we'll go with that. Okay? Yes, sorry, I'm doing this in a different order than I intended, but that's okay. So here is our truck making waves. And here's our truck that's moving, making waves that are bunchy on one side and not bunchy on the other side. So go ahead and draw this picture. You don't have to draw a fire truck. If you like to draw fire trucks, then go for it. But in that space, I want you to draw this picture. So you've got an object that's emitting sound in this case, okay? We're not going to worry about the light part yet. Did you need something? I can help you out. What's that?
We're finishing that thing that we wrote. Oh, yeah.
So as this object is moving, which way is this object moving?
To the right.
To the right?
The frequency is higher. than the first.
It's moving to the right. And the wave fronts, that's what we call these, are bunched up as they get to this person here, who's not standing on the road, to be clear. Always looks like she is, so she's not. She's standing beside the road. She's like, oh, here comes a fire truck, right? And the wave fronts are bunched up, which means what happens to the wavelength?
Shorter.
It's shorter. And then, friends, if the wavelength is shorter, what does that mean happens to the frequency?
Goes up.
It goes up. Yeah. So you're going to write down smaller wavelength. You're going to write down wavelength goes down. And as a result, what happens to the frequency? You just told me. It goes up. Frequency, remember, is just how often. So if you think about it, and we'll watch the video again in just a second, these wavefronts are going to hit her more frequently, more of them per second, than they were before. And that guy that's sad that the fire truck has gone by, oh, there it went, right? The wavelength is bigger there. So as the source moves away, the wavelength goes up, which means what happens to the frequency?
Goes down.
It does. How are we doing physically? Are we doing okay? Okay. What's up?
There you go.
Yep. Just go. Just make it happen. All right. I'm going to keep cruising. Is that okay?
Yeah.
Let's go watch that video a little bit more. You gonna play? Come on, team.
So that is the Doppler effect.
There
The
we go.
apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
How we doing?
So that's how the Doppler effect works with sound. It also affects
We doing okay? Is that making sense? Right? High pitch, low pitch. High pitch when it's coming towards you, low pitch when it's going away. Okay? We'll come back to the other piece that's a misconception in a minute. This is my favorite part.
another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, so there you go. I just think it's adorable. Oh, I didn't mean to do that. Go back. No, please. Just kidding. We don't need to watch whatever this is. Go away. Go away.
Yeah.
Thank you. Okay. So, did you catch what he just said? It's a little bit weird. I want to write down a couple of things. So you've got the object emitting waves moving relative to the observer. We said that if it moves faster, or excuse me, it moves closer to you, then the pitch is going to go up, which means that the frequency goes up. Pitch for sound. Color means that it's turning what color? Not brighter.
Red.
Red shift.
Red.
If it's moving toward you,
Blue.
that means that the wavelengths are getting smaller,
Blue.
the frequency is getting higher, it's blue shift, right? Blue shift if you're moving towards, and what if you're moving away? Red shift. Okay? So that's the key here. We're going to go ahead and take a look at these little charts that I made to make sure that this makes sense, and then I'm going to let you draw some pictures, and then we'll keep cruising. All right. So, if the, okay, let me read this just so I got, so F sub S is the frequency of the source, okay? And F sub O is the frequency that the observer is observing, okay? Before we go on to why this is true, the person that's in the car honking the horn, do they hear the Doppler effect? No.
No.
To them, it's just the whole time, right? But to the person out there, it's going to be a little bit higher before. Right when they're even with them, it's going to be the same note. And then it's going to go lower after, right? So the effect for sound and effect for light, if the frequencies are the same, is no change. Okay. If the frequency of the source is higher than the frequency that the observer observes, you with me there? The frequency of the source is higher than the frequency that the observer observes. What does that mean you're going to hear? The observer is hearing a lower frequency. Tell me what's happening with the pitch. Lower pitch. What about for light? We've said this a couple times, but the more you say it, the more it makes sense. Red shift, right? Yeah.
Is the frequency coming at you different than when it's going away from you? When it's at equal distances far apart from you? So it's coming at you.
If the source is moving relative to you, then yes.
So then why do we say it's a higher pitch coming at you and it's a lower pitch going away?
Because as the source is coming toward you, the wavefronts are getting bunched up together.
Okay.
Bunch. Does that make sense?
Yeah.
And those bunches together mean it's a higher pitch.
So if that truck was in the middle of them, she would still be hearing a higher frequency than...
As long as the truck is moving.
Okay.
If the truck is not moving,
Then it's the same.
then it's this situation, right?
Okay.
If the truck isn't going anywhere, then it's the same. Yes. The only time that you hear the Doppler effect or you see the Doppler effect, the only time the Doppler effect matters is when the source and the observer are moving relative to one another.
Let's say the person was in the car, in front of the fire truck, but they're both going at the same speed. Would the person in the car in front of the fire truck hear higher pitched fire truck if they're going the same speed?
What do you guys think?
I think so.
I think it would be higher pitch and constant the whole time.
So
Like right there.
if the car is here, that's what you're saying?
The car was where the person was at.
So she's in a car
Yeah,
and it's moving this way
to the same speed.
at the same speed. So if it's moving at the same speed, so it depends. I think you have to be careful about at what moment you're talking about it. So if the truck is here and the car is here and it hasn't been moving, then it's going to be a higher pitch. But if they both start driving, right? If you have two cars that start driving the same speed and then the fire truck turns on its engine or turns on its siren, then it's going to sound the same to the person in the fire truck that it sounds to the person in the car. Because they're running away from the sound waves as fast as the sound waves are being emitted.
It's gonna sound the same.
So it's going to sound the same. The same frequency to the car and to the fire truck, not to the person standing next to it. Does that answer your question?
Yeah.
Yeah. There's a lot of math that one can do with this. We're not going to, but one could if one chose to, and I could show you how if you would like to know. But it's not going to be something that I'm going to inundate you all with. Okay. On this sheet here. So then let's do this, the second row of this here. So if the source frequency is less than the observer, so the observer's hearing something at a higher frequency, right, a bigger frequency, then what's the effect for sound?
Higher.
It's a higher pitch. Mm-hmm. And what's the effect for light? What did we say that was? Blue shift. Okay. So this was kind of like, I just wanted to make sure that we're kind of sitting okay. Now I'm going to let you work on these pieces together with your table mates. Okay. So here's the situation. The source is not moving. The observer is not moving. Is there a change in, what's this guy? Wavelength. If so, how does it change? It gets bigger or smaller? Okay. Tell me about the two frequencies relative to one another. And then draw a picture. What is that going to look like? Okay. So just the little like circles and put the source and the observer. You can just put an S and an O, or you can call them A and B, whatever works for you. Okay. I'm going to give you just a couple minutes to work on that because I want to make sure if you can get this, then I know you've got it. And if you have lots of questions, then they'll come up in here. Okay.
Your wavelength, right? So then that frequency is going to be smaller.
Okay, so if there's no motion, then nothing exciting happens, right? I'm going to skip the diagram part, but I just want to say, so there's no change here. If you're moving toward, or excuse me, the source is moving toward you, that means that the wavelength gets smaller or larger? Smaller, which means the frequency for the observer is higher than for the source. Okay? If the source is moving away from you, that means that the wavelength gets bigger, which means that the observed frequency is lower than the source. Maybe I should have flipped those around when I wrote these. I apologize if that's confusing to you. For these last two, the source isn't moving. So this is like your mom or dad is talking to you, they're going, ah, and you are walking away. If you are walking away, that means that the frequency is going to get smaller, right? And that's this one here, walking away, okay? If you're moving toward, that means that the wavelength gets smaller. Moving toward means that the frequency is going to be bigger for the observer. And then if you're moving away, the wavelength gets bigger. The frequency for the observer is smaller. Yes, I'm not going to do the pictures right now because I want to say one other thing really quickly. In this entire conversation about frequency, or excuse me, about Doppler effect, have we mentioned once volume? No. On purpose, how loud it is. Doppler effect has nothing to do with volume. Okay? The volume is going to be only dependent on how far you are away from something. Volume has nothing to do with the Doppler effect.
So when I did that, I was like, it's still the same.
It's the pitch. Yes. So the volume does change, but that's just proximity. Really quickly, I mentioned this at the beginning, but I want to make sure you heard it. We have a quiz on Friday. If you have homework questions over this homework, this is coming directly from Canvas, make sure that you get those done tonight so that I can answer questions for you. We have not done color, so this last little bit of color we haven't done, but everything else should be okay.
Can I point out your source and do my test corrections?
Yeah. For sure.
Same.
Yes, 6,
This is
yes.
my homework.
Cool. Awesome, thank you.
Or during 7th.
During 7th, yes, you may. I'll be here.